Hi class, this is the second video for chapter 12, kinetics. This will cover section 12.3. So I've changed the schedule a little bit. I broke 12.3 and 12.4 into just two separate videos. So this is 12.3, and to make it a little shorter, it will cover worksheets 2 and 3. So I'm going to share my screen right now. We will go to the PowerPoint. So here we go. Let's see what happened. So share screen, PowerPoint. There we go. Okay. So the learning objectives for 12.3, we're going to be covering rate law in this section. So first objective, explain the form and function of rate law. So we're going to figure out or learn how to write a rate law for a chemical reaction. The second, use of the concentration and rates for a reaction to determine the rate constant. So we'll learn what a rate constant is. That's part of a rate law. Then we'll use the rate and concentration data to identify reaction orders. So that's another new term that has to do with rate laws, the order of the reaction. And lastly, use rate laws to calculate reaction rates. So that's one thing that we're not going to do. We have two worksheets in this unit that will cover learning objectives 1, 2, and 3. So let's go. So the rate law expresses the relationship of the rate of a reaction to the rate constant and the concentrations of the reactants raised to some power. So that's a definition of the rate law. Let me move these things out of the way. So if you remember from the last lecture, the rate is equal to the change in concentration over the change in time for the reactants and the products. And those rates are related to the 1 over the coefficient in the equation to each other. So that's how you can calculate 1. If you know the rate of the rate of change of A with respect to time, you can calculate the rate of change of B. So you don't have to do all of them to find out the rates that each one is changing. If you know one, you can calculate the other. So we did that previously. But what does a rate law look like? So the rate law is also related to the rate. So up here we have expressions for the rate. The rate law is proportional to the concentration. We talked about that previously. And so since the rate is proportional to concentration, if you add a constant in there, you can get an equation that equates the rate to this constant. We use this constant times the concentrations of, in this case, the reactants. So oftentimes the rate laws are written in terms of the reactants, but they don't have to be. They can be written in terms of the products also. So the rate law is is equal to the rate constant times the concentration of A raised to a power. Now this power is not the same as the coefficient. You see they're different, so we use different symbols. So in this case, we have K equals the concentration of A, usually in molarity, to the power M. It's not A, sometimes it is, but not always. So we use a different variable symbol here. We would call this, the way we would say this is that this reaction is nth order in A. So the orders that we typically find in a chemical reaction are 0 order, where M is 0, which means A wouldn't even appear because an exponent of 0 is equal to 1, means that value is equal to 1. or m could be 1, which means it's first order, or m can be 2, which is second order. So those are typically what we find: first, zero order, first order, and second order in rate laws. The reaction could be nth order in B. Okay, it could, and the n could also be 0, 1, or 2. Together, you would say the overall rate law, the overall reaction is the m plus n order. So if it's first order in A, first order in B, overall it would be second order. If it's second order in A in second order in B, it would be fourth order overall. So that's how we express in rate. That's how, in general terms, that's how we would write a rate law. So all rate laws take on this form. And remember, the rate is a change in A over the change in T. So we can substitute this quantity for the rate, delta A over delta T, right here. So delta A over delta T would equal K, A to the power M, B to the power N. So let's look at how we can, here's the rate proportional to the bromine. In this case, bromine's a reactant because you can tell it's decreasing. Since it's decreasing, it's reactant. It's a concentration of bromine in molarity at various times. So to write the rate law for bromine, we would substitute this proportion symbol with an equal sign in the K, which is the rate constant. So the lowercase k is always the rate constant. That's the symbol we use for a rate constant. And if you notice, that if we have rate equals K bromine molarity, bromine concentration, that's the equation for a straight line. If we plotted these rates over here, which is rates are always moles per second, they're always positive. We plotted the rates versus the concentrations, you get a line like this over in the right, and that represents this expression of the rate law. Now we can rearrange this rate law to calculate the rate constant. So this is one way. If we know the rates at the different concentrations, we can write this rate constant. And we can calculate the rate constant. We can rearrange this so K equals rate divided by concentration of bromine. This is also going to give us a rate constant, or the units for the rate constant. So this particular reaction that we've written, rate equals K Br2, is a first order reaction. It'd be called a first order reaction in bromine. Because the exponent, the M, equals 1. So there's an understood 1 here. The concentration of bromine is molarity, it's capital M. The rate is molarity per second. So when you have molarity per second divided by molarity, the unit that's left over is per second. So the value, the units that go with K in a first order rate is per second. So we're going to talk more about that later. So let's look. So let's calculate the rate constant. It's shown up here. The rate constant equals the rate over bromine squared, and the unit is 1 over seconds, or seconds to the minus 1. So it's pretty easy. You take the rate. So the first value here, let me get my calculator out, would be 4.2 times 10 to the minus 5. So if I calculate that, 4.2 times 10 to the negative 5 divided by concentration 0.0120, I get 3.5 times 10 to the minus 3. So the rate at time 0 would be 3.5 times 10 to the minus 3. So indeed, that's what we see. In fact, if we do the rate calculations, the rate constant calculation for at every time that we have a rate, we see that it's pretty constant. And that's what rate constant, it's called a rate constant because it is constant. Okay, so if you have the rate law correct, in this case it's first order, the rate constant should be constant. So if we calculated this rate constant and it wasn't constant, it means our rate law is incorrect, that this isn't first order. It would be second order or zero order or something else. So I have a little note here at the bottom that says to do worksheet 2, which has to do with the rate constant. So let me get that out here. So I'm going to switch to a different view. I'm going to end the stop share. I'm going to turn on my notepad view. Let's see what that looks like. Here it is here. Okay, so I'm going to do this full screen, see if that helps. And I'm not sure why you're not seeing that. Let me see. Oh, I know why. So when you're doing this, you need to look at gallery view. Let's see. Okay, there it is. So you need to look at gallery view, and you need to turn on the notepad if you don't see it on your monitor. So that's what I had to do. I have a monitor here. I can see what you see. So unless my monitor is different. So what you want to turn on is the notepad. So let's look at this. So if we this talks about the rate law at the top of this. There's a description. But the worksheet says, for the following data, determine the value of the rate constant at each point in time. Average your values of K to determine the overall rate constant for the reaction. So this is the same same worksheet that was on the slide. So let's do this. 4.2 e to the negative 5 divided by 0.012 is going to equal, let me do this again. This didn't come out right. So 4.2 e to the negative 5 is the rate. I'm going to divide by the concentration 0.012. That's going to give me a rate law of 3.5 times 10 to the, or a rate constant of 3.5 times 10 to the negative 3, and that's seconds to the negative 1. So I wrote that down there. So that's, if you remember, this is exactly the same table of data that we had previously. The average rate constant is going to be about 3.50 times 10 to the negative 5 seconds to the negative 1. And I have, I think, all the solutions on. I have a solution key here, so let's look at that just to be sure. I'll flip the page. There's the answers. If you want to take a screenshot or picture of that, you'll have the answer key. I will post the answer keys to these worksheets at the end of the week. So they'll all be available to you also. If I forget to do that, please let me know. All right, so that's the same table of data that was on the PowerPoint. So let's look at another table of data. This is the same thing. It's a different reaction though. So this reaction says 2NOBr goes to 2NO plus O2. There's a table of data here that has time in the left-hand column, concentrations, and rates. So the rate constant is calculated the same way. So if we say the rate is equal to K times, and that's the concentration of NOBR, NOBR. We know it's NOBR because there's only one reactant. And this is going down, so we know it's a reactant. The concentration is decreasing. I'm going to put here, concentration is decreasing. So we know it's a reactant. Not a product. If it was a product, the concentration would be increasing. Okay, so let's look at the rate constant. So let's do a couple of these. So at 0.086 divided by 0.00592, and our rate constant comes out to be 14.5. Okay, let's do the next one. 0.02868 divided by 0.00063 comes out to be 44.6. And because of the way we calculated it, the unit is seconds to the minus 1. Let's do the next one, 0.016771 divided by 0.000225. That equals 74.5. So something is amiss here. So if you remember, when we're calculating rate constants, they're supposed to be constant. Well, this rate constant obviously is not constant. And so we've got to do something. So if you look at the bottom of this, it says after your above calculations, alter your above calculations to show a different dependence on the reactant. And that is the reactant squared. Okay, so the instructions at the bottom say, let's change our rate law. So our rate law is going to look like this. We're going to change the coefficient. It's going to be K times NOBR squared. So we're changing our rate law to look like that. So that means our rate now, our rate constant then, is going to be K is going to equal the rate divided by the square root of NOBR squared, squared. So let's do one. So that would be, let's do the first one. So I'm going to make a new column here. So this is a new rate constant. This is for NOBR squared, and this was just NOBR. Okay, so we're going to make a new, calculate a new rate constant for a second order reaction instead of a first order reaction. So if I do that, the first value is 0.086 divided by, let me put it in brackets in my computer, 0.00592 squared. And that comes out 2.4. That's not big. Well, it's a pretty big number, 2,453. So I'll round it to 2,450. 2,450. And the unit now, since rate is, let's look at this, let's look at the units. So our K, I'm just going to put in units here to figure out. So the rate is molarity per second, and then the concentration is molarity squared. So molarity cancels. So our rate, the unit for rate constant now is seconds to molarity, 1 over seconds to molarity. So we could write that as m to the minus 1, s to the negative 1. That makes sense. So m to the minus 1, s to the negative 1 equals s, or m negative 1, s negative 1. So those are the units for the rate constant of a second order reaction. So let's try the next one. 0.028068 divided by 0.00063 squared equals, that didn't come out right either. It came out 70,718. I think something's wrong. Let me try this again. 0.086 by 0.00592 squared. Oh, I'm not using the squared. That's what's wrong on my calculator. I'm not using the right button. No, that was right. Squared equals, yeah, 2005. Point 028 8068 divided by 0.0063 squared equals 707.086 divided by 0.00592 squared equals, well, I don't know, it's not coming out right. So I get 2,405 here, I get 770 here, 0.028068 divided by 0.000. Oh, okay. You guys probably saw this right away. I'm doing the calculation backwards. Okay, so I need to divide the rate by the concentration. I was doing the opposite. Sorry about that. 0.00592 divided by 0.086 squared equals 0.80. Okay, so this is wrong. So this is 0.80. Okay, and the unit is per mole second. Let's do the next one. Rate divided by concentration. Come on, Chuck, get that right. Divided by concentration, 0.02806 squared equals, a little better, 0.2 sig figs here because there's only 2 there. Also 0.80. Let's do the third one, just for good measure. 0.000225 divided by rate divided by concentration, 0.016771 squared equals, again, 0.80. All right, so that's the rate. And it's coming out very constant. So this reaction turns out to be a second order reaction. So this is the correct rate law for the decomposition of NOBr. So let's go back to the slideshow. And this completes one of our other goals, learning goals, was to calculate the rate constant from time concentration, and rate data. So we're going back to, let's see, I'm going to stop shares. Come on, stop share. Okay. Go back to check. Stop share, or stop the video of the other. Let's go back to the PowerPoint. That is what I want to do. Okay. Okay, so that's worksheet 2. So let's look at the next slide. So in this slide, we have iodide ion is in acidic solution, and it is oxidized to triiodide ion, I3 minus, and hydrogen peroxide. No, let's say in hydrogen peroxide, iodide, hydrogen iodide is oxidized to I3 and water. So in this reaction, we're going to try to figure out, here's another, a different table of data. So we have 4 experiments here. We have initial concentrations of the reactants, the hydrogen peroxide, the iodide, and the hydrogen. And the goal is to figure out what is the order of the reaction for each of these reactants. So we have the rate, so we have concentrations, and we have the initial rate. But what we don't have is a rate law. So what's the rate law going to look like? Let me see. Put down here. When these data attain the reaction orders, find the rate constant. So we need to figure out the rate law. So let me see if our next worksheet has the same. There we go. Sorry for all that noise. So what you do, you'd write the rate law in generic form with the exponents for hydrogen peroxide, iodide, and the hydrogen ion. And then you would compare the rates when you change. You'll notice that the concentrations here in the first experiment for hydrogen peroxide, iodide, and hydrogen ion are 0.1, 0.1, and 0.05, 0.05 moles per liter, respectively. But in the second experiment, the iodide concentration and the hydrogen ion concentration do not change, but the hydrogen peroxide concentration doubles. So just very quickly, if the hydrogen peroxide concentration doubles, but the others stay the same, look what happened to the rate. The rate doubled. So if the hydrogen peroxide doubles, everything else stays the same, but the rate doubles, it means the order of the reaction for hydrogen peroxide is 1. So that means the exponent over this concentration would be 1. And I'll illustrate that. And the third experiment, the hydrogen peroxide concentration doesn't change from the first one, but the iodide concentration changes. And if you look at what happens to the rate, and the hydrogen ion doesn't change either. If you look at the rate also doubles in the third one from the first one. So that means the order of this reaction is also 1 in iodide. If you look at the third case, we have hydrogen peroxide, iodide are the same as the first case, but the hydrogen ion changes. It doubles. What happens to the reaction rate? It stays the same. That means the order of the reaction in terms of hydrogen ion is 0. So the concentration of hydrogen ion doesn't matter. So we can write this rate law. So I'm going to write this rate law based on this data, and then we're going to do a worksheet. And this will be our third worksheet in this set. I think that's the end of it. So I'm going to stop the share. We're going to go back to our worksheet right here. So that's shown here. So I want to start by going to the previous reaction, write down what we figured out for the rate law. So what we figured out for the rate law. So the rate is equal to the rate constant times the concentration of hydrogen peroxide to an exponent. And we figured that exponent. So if we wrote the generic, we put M, and then the second ion was iodide ion. That was to Mn. And the third ion was hydrogen ion. And that was, we'll say that exponent is O. What we found out from looking at the data, the initial rates at the various concentration is that when you doubled the H2O2 concentration, the rate doubled. So there's a one-to-one correspondence here. So that means the M equals 1. So we can fill in that the rate is going to be the rate constant times H2O2 to the 1. We also found out that the iodide concentration was also 1, and that the hydrogen ion concentration was a 0 order. So the 0, the O there, equals 0. So the hydrogen ion concentration to 0 power is 1. So we don't even include that. So the other thing we can do with that data was that we could calculate the rate constant, because K is going to equal to the concentrations, H2O2 to the 1 times I minus to the 1 divided by the rate. So we had that data there. So that's the other thing we can do with that kind of data, is to calculate the rate. Let me tell you, there are a couple of good examples in your chapter. So this is in 12.3. So in chapter 12.3, I want you to look at examples 12.4 and 12.5. Okay, examples 12.4 and 12.5 are really good examples of how to find the order of the reaction from this kind of data. Right, let's go back and let's just look at this worksheet for a minute. Write the units of the rate constant K for each of the following rate law orders. So the first one is a 0 order reaction. So 0 order reaction looks like this. The rate equals K. The rate just equals K. All right. So let me show you what I'm doing here. Let me see. There we go. Okay. The rate equals K. Remember, the unit for the rate was molarity per second. So the unit for the rate constant is molarity per second. All right. In the second case, so I'm going to substitute the units for rate here. So in first order reaction, we have molarity per second is equal to rate constant times the concentration of molarity to the 1. So that means the K, we look at this, K is going to equal to molarity per second divided by molarity. So the unit for K is seconds to the minus 1. And we talked about that earlier. We said the unit for K was seconds to the minus 1. For second order reaction, and we looked at this also, rate is molarity per second equals K times molarity squared. So that means that K is going to equal to molarity per second times 1 over molarity squared. So if we do that, we get that the units for K are 1 over molarity per second. And oftentimes you see these written like this. Okay, or this could be M S minus 1. Oh, 1.5 order. I'll let you do that one. So you do it the same way, except the order would be 1.5 up here. So you try that one. And like I said, I'll post these answer keys so you can see what it is. Try this one. This is a little tricky. It's a little unusual, but for complex mechanisms, the order can be a non-integer value. Usually it's not. So let's look at example 2. It says you're running a reaction 2A plus B goes to C plus 3D. Your lab partner has conducted the first 2 experiments to determine the rate law for the reaction by the method of initial rates. So these are the 2 experiments. Their initial rates aren't given, but well, those are would have to be measured to be able to do this. But presuming that you can measure the initial rate of each experiment, which of the following concentrations for experiment 3 would help you determine the rate law easily? So there's a few choices here. So A initially is 0.0250, and then they change A to 0.500 molarity. B stays constant for reactions 1 and 2. So that would give us the relationship between concentration of A and the rate. So we probably don't need to change A. So either A would be 0.0500 molarity or 0.02500 molarity. So let's look at our choices down here. So the only ones that would work, we want A to remain constant because we've already looked at A. So we want A to be constant, we want to change B. So the only possibilities are here, C, where A is 0.250 molar, or E, where A is, again, 0.250 molar. So there aren't any choices where A is 0.0500 molar. So let's see what we should do with B. So B here hasn't changed. B is 0.33 molar, which is the same as in the previous 2 experiments. So that's really not very helpful. So I think we can scratch out C. C's not going to help us. If we look at A, or E, the answer E, where we leave A as 0.250 molar, and we change B to 0.660 molar, that means we've doubled B. So that looks pretty good. So if we leave A constant and we double B, we'll get the relationship of the rate to the concentration of B. So the answer in this case is E. So let me circle that. All right, there's one more sheet here. And again, this is same kind of problem. So in this case, it's a reaction of nitrogen monoxide plus hydrogen to give dinitrogen oxide, monoxide, and water. So in experiment 1, in this case, we have the rates here, so that's going to help us. Experiment 1, we have nitrogen monoxide 6.4 times 10 to the minus 3 molar, hydrogen at 2.20 times 10 to the minus 3 molar, and the rate turns out to be 2.55 times 10 to the minus 5 molar per second, which is the typical units for rate. In the second experiment, we have nitrogen monoxide at 1.28 times 10 to the minus 2 molar. So that has doubled, and the rate of the hydrogen stays the same. If you look at the rate constant, it looks like the rate constant, or excuse me, the rate has gone up quite a bit. It's more than doubled. Double would be about 5 times 10 to the minus 5. It may have gone up 4 times. So let's see. So this is a little bit more complicated. So the long, tedious way to do this, if you can't do it by inspection, like if nothing happened, that means it's 0 order. If it doubles, it's first order, but this is more than double. So let's see how we can do that. So we're going to look at rate 1. We're going to just double the rate. So we have rate 1 over rate 2. So we're going to figure this out. And rate 1 is the rate constant times the concentration of NO. I'm going to use the X now. NO to the X times H2 to the Y. And rate 2 is the same thing, K times NO to the X, or H2 to the Y. Now we're going to plug in some values. But first of all, what we can say is if we're comparing rate 1 and rate 2, the only concentration that changes is NO. H2 stays the same, K is the same, so we can cancel these out because those haven't changed. So if I plug in the value for NO in the first reaction, it's 6.4 times 10 to the minus 3 molar. So 6.40 times 10 to the minus 3 molar to the power of X over, and rate 2, 1.28 times 10 to the minus 2 molar, also to the power of X, is going to equal these different rates. And the different rates, rate 1 is 2.55 times 10 to the minus 5, 2.55 times 10 to the minus 5 divided by 1.02 for rate 2 times 10 to the minus 4. So let's do that math and see what we get. So this actually can be simplified. So we can simplify the concentrations. There's 6.40 times 10 to the negative 3 over 1.28 times 10 to the negative 2 to the X. And if I divide those rates, I get 2.55 e to the negative 5 divided by 1.02 e to the negative 4. And that comes out 0.25. 0.25. If I take my 6.40 times 10 to the negative 3 and I divide that by 1.28 times 10 to the negative 2, I get 0.5. So what I have here, I have 0.5 to the power of X equals 0.25. So what is X? So if X is 1, that doesn't work. If X is 2, remember X is probably going to be an integer value. If X is 2, that works pretty well. So if we have 0.5 squared equals 0.25. So we know that X, so X is going to equal 2. Now, if it's not obvious, this is pretty clear. If it's not that clear, you can use logs. So if we took the natural log here, we have the natural log of 0.5. Took the log here, that means we have X the log of 5 equals the log of 0.25. And then X is going to be the log of 0.25 divided by the log of 0.5. And if you do that, we do the natural log of 0.25 divided by the natural log of 0.5, I get 2. Okay, so this is the foolproof way of figuring out x's. You can use logs to figure that out. Okay, so our rate law then in NO is second order. Let's look at H2, the order is. So when we leave NO, let me go back to the original data. We leave NO constant in experiment 3, but we double H2. If we look at the rate, it looks like the rate doubles. So that means it's first order in H2. So our rate law looks like this. The rate is equal to NO squared H2 to the 1. Okay, I have to include my rate constant there. So it's the rate constant, rate equals rate constant times concentration of nitrogen monoxide squared, hydrogen to the first order overall. So it's second order nitrogen monoxide, first order in hydrogen, but overall it's a third order reaction. So I think the other question is, after we get the order of the reaction to each reactant, calculate the rate law constant. So the rate constant then is going to be K, is going to be a rate over the concentration of NO squared times hydrogen divided by hydrogen concentration. So let's just use reaction 1. Let's go back up here. Reaction 1, the rate is 2.55 times 10 to the minus 5. So I'll put down here at the bottom 2.55 times 10 to the negative 5. We can divide it by the concentration of the nitrogen oxide squared, and that's 6.40 times 10 to the negative 3 squared times the hydrogen ion constant, or the hydrogen concentration, 2.20 times 10 to the negative 3, and that's just to the first power. So if we do that calculation, I get K is going to equal to, let me do it, 2.55 E to the negative 5 divided by 6.4 E to the negative 3 squared, divided by 2.2 E to the negative 3 equals, if I calculated right, I get 283. And the unit, this is we have moles per second, or molarity per second, divided by molarity squared times molarity cubed. So our units are molarity to negative 2 seconds to negative 1. So this is a third order reaction. Oops. So what I'd like you to do is try this yourself so you get practice doing it. There are several, when you get to the homework, you'll be asked to do these questions too, and likely you'll have a question like this on the exam. So all you need to do is practice it yourself. So that's it. That's the end of the video lecture for chapter 12.3. And next I'll be working on the video lecture for section 12.4. I'll put that up on Monday. So take care. The class opens officially Monday. You can start working on homework and worksheets and start posting things. So goodbye for now.